This is problem 142 from chapter 12. The race car has an initial speed of 15 meters per second at point A. If it increases its speed along the circular track at a rate of 0.4 s in meters per second squared when s is in meters, determine the time needed for the car to travel 20 meters and the radius of curvature is 150 meters. So it's going around a circular track. And we have the tangential component of the acceleration, which tells us how the speed is increasing. And remember, we also have a normal component of acceleration, which I don't think is going to matter in this problem. And we want to find the time needed to go 20 meters. And because we have the tangential component of the acceleration as a function of position, we're going to use equation 1219. And we're going to integrate. I have the velocity at point A, which is 15 meters per second. I'm finding the time that I need to go 20 meters, so we're going to say t is equal to 0 at point A, and then 20 meters later, so our upper limit of integration here, well, we're actually just going to put it in as s. But if we say s is equal to 20, then we can find the time, which is what we're asked to find. Okay, so I have to put in the 0.4 s, and then I can integrate. And so I pull the 0.4 out. When I integrate s ds, I get 1/2 s squared. I have to put in my limits of integration, but the lower limit of integration is 0. So that just gives me 0 when I plug that in. So 1/2 of 0.4 is 0.2. So that's 0.2 s squared minus 0. When I integrate v dv, I get 1/2 v squared. Then I plug in the limits of integration. I have 1/2 v squared minus 1/2 of 15 squared. Okay, so using this equation seems like the thing to do, and now I have an equation which relates velocity and position, but I'm looking for the time. So if I have velocity and position and I need time, probably I want to use equation 12.1. So let's write that. Equation 12.1 is velocity is the derivative of position with respect to time. And I have velocity here. Well, yes, velocity in my equation here and position over here. But I want to solve this and get an equation for the velocity as a function of position. So, well, I can multiply both sides by 2, then bring the 15 squared over to the other side, and then take the square root. So I get v is equal to 0.4 s squared. That's bringing the 1/2, multiplying both sides by 2 to get rid of the 1/2 on this side. 15 squared is 225, so I'm going to add that to both sides, and then finally take the square root. Now I need to use this equation here to relate velocity and, well, time. So I have velocity as a function of position. What I can do is bring the dt over to the left-hand side and bring the v over to the right-hand side. So I have dt, and then I can take my equation for the velocity and plug it in here, and then I can integrate both sides. So that's going to give me the change in time on the left-hand side. And then I'm integrating 1 over the velocity with respect to position. 1 over the velocity is 1 over 0.4 s squared plus 225. When s is equal to 0, time is equal to 0, I could put in the upper limits of integration as t and s, or I could do t, that's going to be the time that I'm looking for, and I can go ahead and put in the 20, so that will give me the time when s is equal to 20. For this integral, you can use a computer or you can use a table of integrals. And if we have an integral of the form dx over the square root of x squared plus a squared, that's equal to, when we integrate, the natural log of x plus square root of x squared plus a squared. So first I want to take this integral and get it into this form. When I do that, when I rewrite this equation, I'm going to go ahead and integrate what I have on the left-hand side, which just gives me t. So now I have t on the left-hand side. I'm going to pull out a square root of 0.4 in the denominator. That can come outside the integral. So then the first term underneath the radical is just s squared, and the second term, that's going to be, instead of plus 225, that's 562.5, and if you multiply that by 0.4, you should get 225 back again. Okay, so now this has the same form as what I have here. So I have t is equal to 1 over the square root of 0.4, and then I have the natural log of x, but x is what I'm integrating with respect to here. I'm integrating with respect to s here, so that's s plus the square root of s squared plus a squared, which a squared here, so that would be 562.4 for a squared. And then I'm going from 0 to 20. So let's do this again. Okay, so I have square root of 0.4. Then I have the natural log of, when I plug in 20, that's 20 plus the square root of 20 squared plus 562.4, and then I'd be subtracting the lower limit of integration, but remember, when you subtract natural logs, you can instead take the natural log of what you would get by dividing this by what you get when you plug 0 in, which is just 562. This was supposed to be, when I pulled the 0.4 out, this should have been 562.5. So that should be a 0.5, a 0.5, 0.5, and a 0.5. Okay, so then finally we get t is equal to 1.21 seconds, and that is the time needed to go 20 meters.